Hello viewers, how are you? Welcome to my channel Physics with Rams. After a long time we are going to do a new video. So before going to start this video, those who are new to my channel, please subscribe my channel so that you can receive notifications, as well as you can watch my previous videos so that you can clear your concepts and you can solve as many numericals as you can. So in this video we are going to discuss about thermal expansion. If a body expands on heating, then we can represent it as a thermal expansion. So in this video we are going to discuss about the expansion of solids. We know that in the case of solids, they can expand linearly, aerially and volumetrically. So come to the case, when a solid body has been heated, then it can expand along the lengthwise. Then we can represent it as linear expansion. Suppose if the area of the body is being expanded, then we can represent it as a aerial expansion. Suppose if the body volume has been expanded due to heating, then we can represent it as a volume expansion. Volume expansion. Observe that a body can expand along the length or based on the area or based on the volume. So in the case of thermal expansion, for solids we can observe this three types of expansions: length, area and volume. Now we are going to discuss about linear expansion. Observe that in the case of linear expansion, the body is going to expand along the lengthwise due to supply of heat. Let us consider the temperature of the body is T1 degree Celsius. It's initial temperature. Now we had increased the temperature to T2 degrees Celsius. Then the change in temperature is delta T is equals to T2 minus T1. T2 minus T1. Let us consider the initial length of this rod is L1 at T1 degree Celsius and L2 at T2 degree Celsius. Then due to the increase in the temperature, the length of the rod increases. Then the change in the length is represented as a delta L, where delta L is equals to L2 minus L1. Here the change in the length for a solid body is directly proportional to initial length of the rod as well as a change in the temperature. Change in the temperature. So now based on these two equations, here we can represent that delta L is directly proportional to L1 into delta T. In order to remove this proportionality, we have to add a constant where the constant is represented as alpha. Delta L is equals to L1 into alpha delta T. L1 into alpha delta T, where alpha is a proportionality constant, and here we can represent it as a coefficient of linear expansion. Coefficient of a linear expansion. And its unit is per degree Celsius. Unit is per degree Celsius. So observe that delta L is equals to L2 minus L1. So when we substitute this, L2 minus L1 is equals to L1 alpha delta T. So when we bring this L1 towards this side, the expression is represented as L2 is equals to L1 plus L1 alpha delta T. Observe that here we can take L1 as common. When we take L1 as common, the expression is L1 into 1 plus alpha into delta T. So this shows the equation for linear expansion. Or we can also represent it as alpha equals to L2 minus L1 by L1 into delta t. L1 into delta t. This is the expression given for coefficient of linear expansion. So now observe that this solid body can also expand along the area wise. Suppose if we heat a body and it has been expanded based on the area, now we are going to represent the equation. Observe that the initial area of the body is represented as A1 at a temperature T1 degree Celsius, and its final area is A2 at a temperature T2 degree Celsius. So observe that the increase in the temperature is delta T and change in the area or increase in the area is delta A, where delta A is equal to A2 minus A1. A2 minus A1. As we had seen in the previous case, similarly we can represent the present case. So I am writing the expression directly. Observe that A2 is equal to A1 into 1 plus beta into delta T, where beta is coefficient of areal expansion. Coefficient of areal expansion, and its unit is per degree Celsius. Unit is per degree Celsius, or we can also represent the expression as a delta A is equal to A1 into beta into delta T, or we can also represent beta equal to A2 minus A1 by A1 into delta T. A1 into delta. The relation between areal expansion and linear expansion is beta is equal to 2 alpha. This is the relation between areal expansion and linear expansion. Similarly, we can represent volume expansion. So let us consider initial volume of the body is V1 at a temperature T1, and its final volume is V2 at a temperature T2 degrees Celsius. Then the change in temperature is T2 minus T1, and the change in the volume is delta V is equal to V2 minus V1. Then here the expression can be represented as V2 is equal to V1 into 1 plus gamma into delta T, where gamma is the coefficient of volume expansion. Coefficient of volume expansion, and its unit is per degree Celsius. Unit is per degree Celsius. So gamma is equal to delta V, or we can represent it as V2 minus V1 by V1 into delta T. So this is the relation given for volume expansion. The relation between gamma and alpha is gamma is equal to 3 alpha. Gamma equals to 3 alpha. So these are the relations given for linear expansion, areal expansion and volume expansion. Take a screenshot, we will continue. Now we are going to discuss about variation of density with the temperature. We know that density is equal to mass by volume. So here when mass remains constant, we can represent that density is inversely proportional to volume. As the volume increases, density decreases. As the volume decreases, density increases. So since they are inversely proportional to each other. So now come to the case, when we increase the temperature of a body, its volume increases, thereby its density decreases. So based on that, here we can represent that rho dash is inversely proportional to 1 by V dash. Inversely proportional to V dash. Come to the case, when we divided these two equations, here we can represent that rho dash by rho is equal to V by V dash. V by V dash. Now we know that change in the volume V2 is equal to V1 into 1 plus gamma into delta T. gamma into delta T. So in the place of V2 we consider V dash, and in the place of V1 we consider V, where V is initial volume, and due to increase in temperature volume has been changed to V dash. So we consider V2 as a V dash. Then expression can be represented as V dash equals to V into 1 plus gamma delta T. 1 plus gamma delta T. Let's substitute this value in this equation. Then rho dash by rho is equal to V by V into 1 plus gamma delta T. So now V gets cancelled. Then rho dash is equal to rho by 1 plus gamma delta T. This shows the relation between final density and initial density. Or we can also represent the expression as rho dash equals to rho into 1 plus gamma delta T whole to the power of minus. Also that it is in the form of 1 plus x whole to the power of n. By reducing it to lower terms, it can be represented as 1 plus nx. Then the density expression is rho dash equals to rho into 1 minus gamma into delta T. So this is the relation given for final density and initial density due to the increase in temperature. Take a screenshot. We will continue. Now we are going to discuss about effect of temperature on a body when it is moving in a liquid. So here I am going to consider a body within the liquid. Here the weight of the body will be acting in the downward direction. And here if the body is, if this block is moving in the upward direction, then pseudo force will be acting in the downward direction. Then weight of the body can be given as m into g plus a, m into g plus a. And upward thrust will be acting in the upward direction. Upthrust will be acting due to the liquid. So here the upthrust is represented as F. In this case, the apparent weight is represented as W apparent is equals to actual weight minus upthrust. Actual weight minus upthrust. This upthrust is represented as F is equals to mg. F equals to mg, where density is equals to mass by volume. Then mass equals to density into volume by using this expression. So as we substitute this, the force can be represented as a density into volume into acceleration due to gravity. So since it remains constant, here we can represent that the thrust force is directly proportional to density into volume. Density into volume. So this is the thrust acting at a particular temperature. Suppose if we increase the temperature of the body, then the thrust is represented as F dash. F dash is directly proportional to rho dash into V dash. Now when we divide these two equations, then expression can be represented as F dash by F is equals to rho dash V dash by rho into V, where we already had seen the expression for rho dash. Rho dash equals rho by 1 plus gamma L, expansion of the liquid due to increase in temperature, into delta T. Whereas V dash is equals to V into 1 plus expansion of the solid due to increase in the temperature. Now let's substitute these two values in this expression. Answer that F dash by F is equals to rho dash equals to rho by, or density of the solid, by 1 plus gamma L into delta T, into density of the solid. So here density of the solid gets cancelled, into, after that V dash equals V into 1 plus gamma S. So when we substitute this, V into 1 plus gamma s into delta t by v. Observe that v gets cancelled. Then f dash by f is equals to 1 plus gamma s into delta t by 1 plus gamma l into delta t. So this is the relation given for upthrust due to the increase in temperature based on volume expansions. So here let us consider that the expansion of the solid is greater than expansion of the liquid. As you compare this, here we can represent that f dash is less than f. Based on that, here we can represent that apparent weight is greater than actual weight. Apparent weight is greater than actual weight. Come to the case. Similarly, if we consider if expansion of the solid is equals to expansion of the liquid, then forces will be same. Then here we can represent that apparent weight is equals to actual weight of the body, actual weight of the body. Take a screenshot, we'll continue. Now we are going to discuss about the time period of oscillation of a pendulum is represented as t is equals to 2 pi into under root of L by G. Now when we heat this pendulum, the time period will be changed to t dash. T dash equals to 2 pi into under root of L dash by G. So now based on that, here we can represent that t dash by t is equals to, also that 2 pi gets cancelled and G also gets cancelled. So expression is L dash by L. Observe that L dash is nothing but length of the pendulum after increasing the temperature from T1 to T2 degrees Celsius. So here the expression can be represented as L dash equals to L into 1 plus alpha into delta theta or delta T small t, delta small t. So here when we substitute this in this expression, the equation can be represented as t dash by t is equals to L into 1 plus alpha into delta t by L. Observe that L gets cancelled. So expression can be represented as t dash by t is equals to 1 plus alpha delta t whole to the power of 1 by 2. It is in the form of binomial expansion. When we reduce it to lower terms, we can represent it as 1 plus nx. Observe that t dash by t is equals to 1 plus 1 by 2 alpha delta t. Then t dash equals t into 1 plus 1 by 2 into alpha into delta t. So this is the expression for time period of the pendulum due to increase in temperature. Take a screenshot. We will continue. Let's solve numericals based on the concepts which we had discussed in this video. Observe the first one. A seconds pendulum clock has a meter wire. The clock is calibrated at 20 degrees Celsius. How much time does the clock lose or gain in 1 week when the temperature is increased to 30 degrees Celsius? Here the temperature has been increased to 30 degrees Celsius. Initial temperature is 20 degrees Celsius and then increase in the temperature is T2 minus T1, nothing but 30 minus 20 equals to 10 degrees Celsius. So now here we have to find the final time period. Whereas since we had considered second pendulum, the initial time period is represented as 2 seconds. 2 seconds. Then T2 is equals to T1 into 1 plus half alpha into delta T. 1 plus half alpha into delta. So here alpha represents a linear expansion, where alpha of a steel is 1.2 into 10 to the power of minus 5 per degree Celsius. So when we substitute this, observe that 2 into 1 plus 1 by 2 into 1.2 into 10 to the power of minus 5 into 10. Here, as you observe this expression, 1 plus 0.6 into 10 to the power of minus 4, or we can represent it as 2 into 1 plus 6 into 10 to the power of minus 5, or we can represent it as 0.00006. So 1 plus 2 into 1.00006. When we multiply it, it can be represented as 2.000. 6 to 12 seconds. So this is the increase in time period. Now we have to represent the time lost in 1 week. For that, we have to represent the change in time period. Observe that the change in the time period delta t is equals to t2 minus t1. t2 minus t1, which is nothing but 2.00012 minus 2, or here we can represent it as 1.2, because 3 and 4, 10 to the power of minus 4 seconds. So this is the change in time period, change in the time period. Now we have to find the time lost or gain in 1 week. Since the time period has been increased, the time will be lost. It takes more time to oscillate. Then the time lost in 1 week can be given as a delta t is equals to change in the time period by original time period into 1 week, 7 into 7 days. And we know that for every day we have 24 hours, and for every hour we have 3600 seconds. And substituting the values and simplifying this, here we get a value of 36.58 seconds. So this is the time lost by the pendulum. Next, observe the second problem. A steel ruler exactly 20 centimeter long is graduated to give correct measurements at 20 degrees Celsius. It shows the correct reading at 20 degrees Celsius. And length of the steel ruler is 20 centimeters. So observe the first one. Will it give readings that are too long or too short at lower temperatures? As the temperature decreases, the length of the ruler also decreases. Thereby, the readings will be short. It will not be long. Why? Because it has contracted, not expanded. So it shows short readings. And next, observe what is the actual length of the ruler at 40 degrees Celsius. So now we have to find L2, where L2 is equals to L1 into 1 plus alpha into delta. Already we had seen the linear expansion of steel is 1.2 into 10 to the power of minus 1. So when we substitute this, initial length is 20 centimeters. So 20 into 1 plus alpha is 1.2 into 10 to the power of minus 5 into increase in the temperature. 40 minus 20, 20. 40 minus 20 is 20. So when we substitute this, 20 into 1 plus 1.2 into 2 is nothing but 2.4. 2.4 into 10 to the power of minus 4. Or we can represent the expression as 20 into 1 plus 2.4 into 10 to the power of minus 4, nothing but 0.00024. 2.4 into 10 to the power of minus 4 can be represented as 0.00024. So here when we add this, the expression can be represented as 20 into 1.00024. So 20 into 1.00024, when we multiply this, 4 2s are 8, 2 2s are 4. Due to 20, here we can move 1 point and 2 1s are 2. 20.004. Centimeters. This is the length of the steel ruler at 40 degrees Celsius. take a screenshot. Please give a like to this video, share this video to your friends, and don't forget to subscribe my channel.